Welcome to AI Paper Slop, the YouTube series, where we summarize the absolute bleeding edge of AI and tech papers so you can stay up to date.
Hey everyone, great to be here.
So let's jump right in. Today we are doing a deep dive into a really incredible breakthrough in LLM Post-Training.
Yeah, this one is from researchers at Peking University, Xiaomi, and a few others.
Right, and the paper is titled MOPD, Multi-teacher On-Policy Distillation for Capability Integration in LLM Post-Training.
It's a bit of a mouthful, but the core insight is actually so elegant.
Completely. For the first minute here, let's just give you the absolute core takeaway. If you're building an LLM and you want it to be amazing at math and software engineering and instruction following, combining those capabilities usually degrades the model's performance.
Oh, massively. Or it requires incredibly unstable parameter merging.
Exactly. So this paper solves that with MOPD. They basically train domain-specific RL teachers in parallel.
Right. Totally separate from each other.
And then they use on-policy distillation. The student model generates its own rollouts and gets token-by-token scoring from the relevant frozen teacher.
Which is huge because it entirely eliminates exposure bias. It gives you this incredibly dense optimization signal.
And maybe best of all, it allows parallel engineering teams to just work without blocking each other. On their Quen 330B test, it recovers over 91 to 95% of all the specialized teachers' capabilities.
It absolutely crushes the Mix-RL and Cascade RL baselines.
It really does. So let's unpack this architecture, because before we get into how MOPD actually works, we kind of need to talk about why integrating capabilities has been such a nightmare for ML teams.
The graveyard of existing methods, basically.
Yeah, exactly. I mean, if you're managing a training cluster, you've probably tried to integrate capabilities using one of like 4 standard approaches.
And you've probably hit a wall with every single one of them.
Right. So let's start with Mix-RL. Intuitively, you just take your prompts from every domain: math, coding, creative writing, put them in one data set, and train.
Right, which sounds fine until you actually look at the loss landscape.
Because they're completely different, right?
Exactly. A verifiable math problem has a very strict step-by-step logical path. The loss landscape is incredibly spiky.
But instruction following is much smoother.
Yeah, it's open-ended. So when you batch these together, the gradient updates are pulling the model weights in diametrically opposed directions.
Creating this massive seesaw effect.
Right. Optimizing one capability actively degrades another. You usually end up with a model that performs worse than your specialized baselines.
So if batching them together fails, the logical next step is Cascade RL. Train them sequentially.
Right, so instruction following, then math, then software engineering.
But then you just get catastrophic forgetting.
Oh, completely. By the time you're fine-tuning on software engineering, the weights required for instruction following are just, they're gone, overwritten.
Plus, chaining all those massive RL runs together. If a node fails in month 2, your sunk costs are just staggering.
The stability risks alone make it unviable for most teams.
Okay, so then people try off-policy fine-tune. Just use the RL teachers to generate millions of perfect rollouts and teach the student to mimic them with SFT.
Right, offline imitation learning. But the fatal flaw there is exposure bias.
Because the student only ever sees the golden path, right?
Exactly. It memorizes perfect trajectories, but during inference, the moment it makes a tiny mistake, say it hallucinates a variable name, it enters a state space it has never seen.
Yeah, and it just panics.
It has no idea how to recover. The trajectory just drifts wildly away from the training distribution.
Which leaves us with the weird one, paramerge. Weight space fusion. Task arithmetic, model soups, basically averaging the weights of specialized models.
Which is, well, it assumes the weights remain in the same linear basin.
But RL pushes them way outside that basin, right?
Yeah, RL drastically alters the weights. If you try to linearly interpolate them, you usually land in a region of super high loss.
It's just so unpredictable. It feels like we've been trying to assemble an Avengers team of models, but doing it terribly.
That's actually a great way to put it.
Like Mix-RL has them all just talking over each other in the same room. Cascade RL trains them one by one, but they immediately forget everything.
Right. And off-policy is just having them read each other's diaries.
Yeah. And paramerge is like trying to genetically splice them together in weight space, which just creates a monster.
Literal weight space monster.
Yeah.
The loss landscape just doesn't support it. You're always trading off learning efficiency against peak performance.
So if weight space and static data sets are dead ends, MOPD says we have to do this in policy space.
Exactly. Abandon weight merging entirely. MOPD relies on prompt routing across 3 distinct stages.
Okay, let's break down the pipeline. Stage 1 is general SFT, right?
Yes, you fine-tune your base model on a broad corpus. But the real function here is creating a shared initialization point.
Okay, so this single checkpoint is the seed for everything else.
Exactly. It demonstrates basic competence everywhere, and you use it to initialize both the teachers in Stage 2 and the student later in Stage 3.
That brings us to Stage 2. Domain-specialized RL. This is where I'd imagine big labs get really excited.
Oh, for sure. Engineering teams get to operate in total isolation here.
So the math team can just build their verifiable answer RL pipeline, completely ignoring the coding team.
Right. They don't have to coordinate hyperparameters or balance data sets. They just optimize their specific teacher model to the absolute limit.
You're completely decoupling capability production from integration.
Exactly. You end up with these highly specialized frozen teacher models.
Which sets up the crazy part, Stage 3, the MOPD distillation phase.
Right, where the magic happens.
The student initializes from that Stage 1 checkpoint samples a multi-domain batch and starts generating trajectories. And then the prompt routing kicks in.
Yep. If it's a math prompt, the generated rollout gets routed to the frozen math teacher.
And the teacher basically pre-fills the student's trajectory to provide token-level log probabilities.
Yes. Instead of just getting a pass-fail reward at the very end, the student gets dense token-by-token supervision.
Okay, wait. If I'm an infrastructure engineer listening to this, I am sweating right now.
Oh, I know what you're going to say.
Routing every single student rollout through a massive 30 billion parameter frozen teacher just to get token probabilities, doesn't that create massive serial latency?
It sounds like a total nightmare.
Like you're basically having your throughput if the RLO has to pause and wait for that forward pass.
Right, and that's exactly why on-policy distillation has historically failed to scale. But they engineered a brilliant workaround.
Okay, how did they fix it?
They don't put the teacher prefill in the RL training loop. They use standalone asynchronous prefill services on separate GPUs.
Oh, so they communicate via RPCs, remote procedure calls.
Exactly. The student sampler never stops. The moment it finishes generating a sequence, it fires off an async request to the teacher service.
And it just immediately pulls the next prompt.
Doesn't wait for a second, it just keeps generating. Meanwhile, the teacher node receives the completed sequence.
And since it's a known sequence, it can just do a highly parallelized prefill pass.
Which is vastly faster than autoregressive generation. It calculates the log probs, ships them back, and the latency is entirely hidden behind the student's own generation time.
That is so elegant. You're just hiding the massive compute cost in the shadow of the student sampler.
Yeah, the wall clock cost is dominated entirely by the student.
So the async infrastructure solves the compute bottleneck. But what's the actual math for the gradient signal? How does the student update its weights?
Well, the goal is to minimize the per-token reverse KL divergence between the student and the teacher.
But evaluated strictly along the student's own trajectory.
Exactly, which completely solves the exposure bias problem from earlier. The student learns to navigate the space it actually visits.
So they offer two implementations for this, right? Let's start with the policy gradient one.
Yeah, this one is super straightforward. You just take the log difference between the teacher's probability for a token and the student's probability.
And you just treat that as a per-token advantage.
Exactly. If the teacher thinks a token is highly probable and the student doesn't, you get a positive advantage.
So it pushes the student to increase that probability, and you clip it for stability.
Yep, just like in proximal policy optimization, or PPO. The beauty is that this drops directly into existing RL frameworks.
You're just changing like one line of math in your code base.
It's incredibly accessible.
But what if you're running a frontier scale model? If my vocabulary is 100,000 tokens, shipping full probability distributions over RPC is going to saturate my network instantly.
Oh, it would absolutely choke the bandwidth. That's why they introduced the top K distillation method.
Okay, so they don't send the full distribution.
Right. The teacher only returns the logits for its top K tokens.
Yeah.
In the paper, they use the POP 64.
Wow. That reduces the network payload by what, over 99%?
Easily. It becomes this incredibly lightweight payload.
But hold on, mathematically that shouldn't work. If you just minimize KL divergence against a truncated distribution, the student is going to over-index on those 64 tokens.
And it would assign zero probability to the rest, yeah.
Right. You're breaking the fundamental normalization of the probability distribution.
You are entirely correct. And if they hadn't fixed that, the model would have diverged completely.
So how do you correct the truncation bias?
They add an extra term to the top K loss function, They basically group all the discarded long-tail tokens into a single aggregate probability mass.
Oh, I see. So you calculate that aggregate mass for the teacher and for the student.
Exactly. And the extra loss term explicitly minimizes the difference between those two masses.
That's brilliant. It keeps the long tail perfectly calibrated while pulling the student toward the top 64 preferences.
It prevents the distribution from artificially collapsing.
Just to ground this for the listener in standard RL, your model generates thousands of tokens of code, and at the end, it just gets a 1 or a 0. Did it compile?
Which is such a sparse, weak signal.
Right. The model has to guess which of those thousands of keystrokes actually mattered. But MOPD is it's like having a senior engineer doing live pair programming with you.
Grading every single keystroke in real time.
Yeah. This variable is great, this loop is slow, that dense signal must drastically reduce the variance of the gradient updates.
That is exactly the key, variance reduction, and you see it immediately in the empirical benchmark.
Let's talk about those benchmarks. They tested this on the Qwen 3 30B A3B architecture.
Across 3 really tough domains. Math, using AMI, instruction following, and software engineering using SWE Bench.
And they used a normalized score, right? Where 0 is the base model and 1 is perfectly matching the specialized teacher.
Right. And MOPD hit an average normalized score of 0.937.
That's insane. It's uniformly recovering 91 to 95% of the headroom.
Yeah, compare that to Mix-RL, which peaked at 0.882, but had severe per-domain weaknesses because of that seesaw effect.
And Cascade RL was way down at 0.775 because of the forgetting. But the metric that really blew my mind was the sample efficiency.
Oh, it was a massive win for ML engineers.
Because of that dense token-level tutor, MOPD hits the teacher's plateau on instruction, following, about 25,000 samples?
Yeah, 25K. And software engineering in just 30,000 samples.
If you're an ML manager, you need to realize what a 5x to 6x reduction means. Mix-RL took up to 180,000 samples per domain.
Hitting convergence at 25K samples means freeing up your GPUs weeks earlier.
You're saving literally millions of dollars in compute overhead.
And they proved it scales at industry levels, too. They applied this to the 309 billion parameter MIMO V2 Flash model.
309 billion, that's a massive stress test for the async infrastructure. Did it hold up?
Flawlessly. They expanded it to include tool use as well, and it consistently matched or exceeded the frontier teachers.
Wow. Wait, I remember on the AMI math benchmark, the MOPD student actually scored 94.1, beating the specialized math teacher's 93.9.
Yeah, the scaling laws just hold up perfectly.
Which actually leads us perfectly to my favorite part of this paper, the ablation study. Because traditional distillation is famously unstable, right? You get mode collapse, policy entropy goes crazy.
But MOPD is smooth because of a strict rule they discovered called the same origin principle.
Right. So the researchers asked a very natural question. What if we use an even smarter external teacher?
Yeah, they swapped out their 30 billion parameter same origin math teacher for a massive 235 billion parameter model.
Logically, a better tutor means a better student, right? But the training just collapsed.
It was catastrophic. In the top K variant, the whole thing fell apart around step 18. Wild entropy oscillations, complete divergence.
Why does a smarter teacher destroy the student? Are the latent representations just too alien?
It comes down to the initial KL divergence. Because the standard teachers and the students share that stage 1 initialization point, their probability distributions are highly aligned.
So the initial KL divergence is low.
Yeah, it was a very tight 0.04. But the 235 billion model had a totally different training history. Its initial KL was nearly 5 times higher at 0.19.
Ah, so when the student generates a rollout, its state space makes sense to itself, but the alien teacher looks at it and says, this is highly improbable.
Exactly. So the student receives purely punitive signals. The teacher assigns massive negative advantages to almost everything.
It's basically screaming that everything the student does is wrong, but it doesn't offer a constructive path forward.
Right. The teacher's high probability regions are just too far away. The student's policy entropy violently contracts to escape the penalty, and it just panics and diverges.
So the same origin principle says you absolutely must use teachers derived from students' own initialization point?
Yes. That ensures the students' rollouts actually land in the teacher's high probability regions, which gives you constructive gradients.
But doesn't that put a hard ceiling on how smart the model can get? If we can't bring in external genius models, how do we push the frontier?
That leads to the final and maybe most profound part of the paper, multi-round evolution.
Okay, how does that bypass the ceiling?
You bootstrap it, You take the output of your first MOPD integration, that fully unified student that absorbed all the initial headroom.
And you use that unified model as your brand new stage 1 baseline.
Exactly. You elevate the baseline, then you spin up a second generation of isolated domain RL training.
Oh, wow. And because they start from a stronger base, they can push the optimization even further in their domains.
Right. The Iteration 2 RL teachers hit a normalized score of 1.030 relative to the first iteration.
New headroom unlocked. And because they share an origin with the new baseline, you can safely run MOPD stage 3 again without any entropy collapse.
Exactly. You distill them back into a new Iteration 2 student, which smoothly jumped to a 0.986 normalized score.
It's like an iterative expectation maximization algorithm in policy space. Establish a baseline, expand through isolated RL, compress back into the core.
You can theoretically repeat this loop indefinitely, keeping it stable every single time.
Zooming out, this is way more than just a clever loss function. It structurally decouples how AI labs operate.
Total risk isolation.
Exactly. Your math team and coding team don't have to argue over a fragile joint RL recipe. If the coding team's run fails, they just restart their isolated teacher pipeline.
The multi-domain run is perfectly safe. Integration only happens when everyone's expert is fully baked.
It's such a mature, modular approach to engineering intelligence, which leaves us with a truly provocative thought for you to ponder.
Oh, I like where this is going.
If we can successfully execute this multi-round evolution, expanding and then compressing what happens when we fully automate that loop.
Right, without human engineers manually gating the stages.
Imagine a future architecture where an LLM continuously self-specializes. It spawns thousands of microdomains during the day, running sandbox RL to master hyper-specific tasks.
And then automatically distills them back into a single omni-capable core model overnight.
Exactly. It mirrors how the human brain consolidates specialized daily experiences into generalized knowledge during sleep. If MOPD stabilizes that evolutionary loop, the ceiling for continuous self-improvement is basically non-existent.
The infrastructure's definitely there to support it now.
It's just a matter of how fast we can generate the specialized domains. Well, we will certainly be keeping our eyes on how this scales. Thanks for joining us for this deep dive into the MOPD architecture. We'll see you next time.